Alright, so we are now starting the exercises based on the notion of homomorphism. So let's see this one. Here we are given two maps, two functions alpha and beta in two different situations. We have to decide whether each one of them is a homomorphism, and also if it's a homomorphism, then we have to further see if it is one to one and onto. Okay, so let's see. In the first one, the first group G is the group of all positive real numbers under multiplication, and the second group H is the additive group of all real numbers. And the function alpha from G to H is defined by this formula. Alpha maps A onto the logarithm of A to the base 10. Okay, so let's see the solution. We know that this function is well defined because every positive real number, keep in mind that here the inputs are positive real numbers. G is the group of positive real numbers under multiplication. Now we know that every positive real number has a unique logarithm to the base 10. Okay, so that means this function is well defined. So we can now see whether the condition for homomorphism is true for this function or not. Let A and B belong to G. So that means A and B are both positive real numbers. Now we are going to see what happens to the alpha image of AB, and here AB means actually the product of the real numbers A and B. By definition it's just log of AB, and from elementary properties of logarithmic function we know that this is log A plus log B. Okay, logarithm turns multiplication into addition, but log A is alpha of A and log B is alpha of B. So that means the condition for homomorphism in this case is true, because just like here we have the operation in G which is multiplication, here we have the operation in H which is addition, because the second group is the additive group of all real numbers. So alpha is a homomorphism. Okay, so the next thing to see is whether alpha is 1 to 1 or not, and then we will also see whether it's onto. For C and D in G, let alpha of C be equal to alpha of D. Then log C to the base 10 is equal to log D to the base 10. So that means these two real numbers are actually the same. So these powers will also be the same. and from properties of logarithms we know that this is nothing but c, just like that this is d. So having assumed that the outputs of c and d under alpha are equal, we have obtained that the inputs are also equal. So alpha is 1 to 1. Either you can arrive at the one-to-oneness of alpha just like this, or there is another way. Since you have shown that this is a homomorphism, you can calculate the kernel of this homomorphism, and from a result of this section you know that alpha is 1 to 1 if and only if the kernel is the trivial subgroup of the domain group. In this case, you will see that the kernel consists of only the identity element in the first group. Because the first group is the multiplicative group of positive real numbers, that identity element will be 1. That way also you can approach one-to-oneness. So I suggest you try that. Okay. Here, however, we have just simply shown that the function is 1 to 1. That's it. Next, for ontoness, let us take any element from the second group. Next, let R be any element in H. That means R is any real number. Then 10 to the power R belongs to G. Note that from properties of powers, we know that regardless of the sign of R, that is whether it is positive or negative, it can be 0 also. 10 to the power R is a positive real number. Okay, so that is why it belongs to G. And what is the alpha image of 10 to the power R? And the alpha image of 10 to the power R by definition is this. And then you know from properties of logarithm, either you can just directly write R here, or you can bring R in front of log, and then using the fact that log 10 to the base 10 is 1, that way also you can get R. Anyway, you just get R. So that means any real number appears as the output of alpha for some input. So that means alpha is onto. And that completes part 1. In part 2, our function is from the group of integers to itself. Group of integers means the binary operation is addition, that is understood. The set of integers does not form a group under multiplication. And what is the function? The function maps any integer a to a plus 1. This is not a homomorphism because it violates one of the necessary conditions for a function to be a homomorphism, which is that if a function is a homomorphism, then it has to map the identity element of the domain group to the identity element of the codomain group, that is that other group, which is not the case here. Since 0 belonging to the set of integers is the identity element, and in this case the function is named beta. Beta of 0 is equal to 0 plus 1, which is not equal to 0. beta is not a homomorphism. Of course, you can also show that beta does not satisfy the actual condition that we require in a function for it to be a homomorphism. But this is a neat way of showing that it's not a homomorphism. Similarly, whenever you are asked to show that something is or is not something, okay, and say you have somehow understood that it should not be that thing, then you just try to show that one of the sufficient conditions is violated, just like this. Okay, so that would be neat. And that's it. So if it's not a homomorphism, we need not see whether it's one-to-one or according to the exercise. Now let's see the next one. Let alpha from this direct product (27) into Z27 be given by the function is defined by a rule and that rule is just this: alpha of the ordered pair A comma B is equal to 3B. The reason for having two sets of parentheses here is that this ordered pair A comma B is an element of the domain group, and the outer parentheses enclose that element, which we normally do in a function. That's why we have two sets of parentheses. For all, okay, yeah, obviously, for all A in Z9 and B in Z27, show that alpha is a homomorphism. Okay. So that's the first thing we have to show, and then also find the kernel of alpha. So here we have to find the kernel and decide if alpha is onto. The kernel has nothing to do with ontoness of alpha, so that means we have three things to do. Let's see. So for homomorphism, same thing. You just take two elements, compose them in the domain group, and apply alpha on that, and then see what happens. So we are going to consider two elements here. Then alpha of A comma B, C comma D. Alpha of A plus C comma B plus D, that is equal to, so according to the definition of our function, this is 3 times the second coordinate. That means 3 times B plus D, which is 3B plus 3D, and that is equal to alpha of A comma B plus alpha of C comma D. Okay, let us now justify the steps of this calculation. You see, we haven't written plus here. If you want, you can write plus. That will just denote the binary operation in the domain group, which is the direct product of Z9 and Z27. Why are we justified in using plus? There is a reason for that, because that group is an additive. Additive group means it's an abelian group. Okay, so we can use the addition as the symbol for the binary operation in the group. But I have chosen to not do that. Okay, we can just simply not write anything to denote the binary operation. But you know what the binary operation is according to the definition of direct product of two groups. So according to that definition, the result of this product of A comma B and C comma D is A plus C comma B plus D, where this plus is happening in the first factor, that is Z9, and this plus is being carried out in Z27. In other words, this binary operation is addition modulo 9. This one is addition modulo 27. Okay. And alpha of that by definition is this. Now this is addition modulo 27, but we know that in Z27 and in fact in other such groups, this type of distributive law is still true. Okay, because these are not just groups, but these are rings also. We will see what those things are later on when the time comes. But anyway, this is true. And then the rest is just usual. So that's why alpha respects the binary operations in the two groups. So alpha is a homomorphism. Next, we have to find the kernel of alpha. So for that, let us take any element in the group actually. Then U comma V belongs to the kernel of alpha if and only if alpha of U comma V is equal to 0, and that 0 is because our second group, the codomain group, if you want to call it that, Z27, so it is that thing, the 0 element of that group. And this implies and is, it's equivalent to having 3V equal to 0. Okay. Now in Z27, what type of V's precisely satisfy this equation? What the V's are that satisfy this equation? It's not just V equal to 0, but there are I mean, there are, besides b equal to 0, there are other solutions also. And those solutions are precisely this, which one can of course find by looking at all the cases 0, 9 and 18. Okay, so as these, these are elements in the 27. So that's why this is the kernel. Well, I should not say that this is the kernel, but the kernel consists of those ordered pairs where the second coordinates come from this. So let us write these things properly. The alpha image of u comma v being 0 is unaffected, actually unaffected by what u is. So u can be anything. So kernel of alpha, because of that fact, kernel of alpha can be written like this. Where it is understood that this is considered as a subset of C27. Okay, so you can, although we have nothing to say about, or we are not supposed to say about whether alpha is 1 to 1 or not, but still alpha is not 1 to 1, we can say, because the kernel consists of things other than the identity element in the domain group. If you want, you can write that conclusion. Note that this implies that alpha is not 1 to 1. Okay, so now next we look for ontoness. And alpha is not onto as well. Let's see why. Suppose that for some, how should I write it? That for some u comma v in the domain group, alpha of u comma v is equal to 1. 1 as an element in Z27, that is the second group. Then three v is equal to 1, which implies nine times 3v equal to 9, or (27v) equal to 9, or because the calculation is happening in Z27, so 27v is 0, 0 equal to 9. But this is impossible in our system. In this system 27 is equal to 0, but 9 is not equal to 0. So our supposition is wrong, and hence, so if 1 does not have an inverse image under alpha, that tells us that alpha cannot be 1 to 1, cannot be onto possibly, and hence alpha is not onto. So this is an example of a homomorphism that is neither 1 to 1 nor onto. Okay. So that's the end of the solution. Let's see another one, the next one. Define alpha from U16 times U16 into U16. We know what the U16 group is via alpha of A comma B, because we are again considering a direct product, so the input will be an ordered pair. This is equal to alpha, alpha is the function, A is the element, AB inverse. Okay. Show that alpha is a homomorphism and find alpha inverse of this. That means this cyclic subgroup generated by 7 in this group, and the second group is a subgroup of the second group. Its inverse image under alpha we have to find, but before that we have to show that it's a homomorphism, which is rather easy. Again, like before, let us take two elements. But this time in this direct product. Although I may not say this every time I encounter a function, but the moment I see a function, I see whether it's well defined or not, whether it's really a function or not. You should also do that, because if something fails to be a function, then with that we cannot do, we can do other things, but not what we are doing here. Okay, so this is also a well-defined function. I am not going to say anything more on that. Then alpha of A comma B, C comma D. So here also this binary operation has a precise meaning, which is just simply this AC comma BD, where between A and C we have the operation in U16, and between B and D also the same operation, because the same group in this case. And now by the definition of alpha, this is AC BD inverse. Okay. Now, in general, BD inverse in a group, in what group in this case? In the group U16, because these are after all individually elements of U16. So, ultimately this is again a product in U16. There, in general in a group, it will be D inverse, B inverse. But because we know that U16 is an abelian group, so we can change order as we wish. B, so you can write B inverse, D inverse also, because now also we have to change order. C, D inverse. The fact that this is possible because U16 is abelian, of course, need not be mentioned, because that is something one can see easily. You will realize what to mention and what not to mention as you work with these things more and more. Now the first part is alpha of A comma B, and the second one is alpha of C comma D. Thus alpha is the homomorphism. Okay, next we have to find this. So let's see how that can be done. Well, you can, if you want, you can actually write down all the elements in this cyclic group and then find the inverse images of each one. That way also you can do, or you can proceed like this. Let U comma V belong to the domain group. Then let me write like this. U comma V belongs to alpha inverse of this if and only if, by the definition of inverse image, alpha of U comma V belongs to this. Now in U16, it turns out that this cyclic subgroup has only two elements. One of them is 1, the identity element, and the other one is 7, because in U16, 7 has order 2. So by the definition of alpha, this is UV inverse, and that should belong to this, that is UV inverse is equal to 1 or UV inverse is equal to 7. You can further simplify the situation even more. U is equal to V or U is equal to 7V. So that means having this element in the inverse image is equivalent to having either U equal to V or U equal to 7V. Now from these conditions we will get these elements. This immediately tells us that the ordered pairs where both the coordinates are equal are going to be elements in this inverse image. So with that in mind, we can start writing the inverse image. Keep in mind U16 That means U16 has all the positive integers less than 16 and relatively prime to 16. That means it should be relatively prime to 2. Okay, so no even integer will appear. So these are the elements that satisfy this condition. But what are the elements that satisfy the other conditions? And they are these. 1, 7, 7, 1, then 3, 5, 5, 3. It's found that whenever u comma v is there like this, then v comma u is also there, which in this case does not give us any new element. Then 9, 15, 15, 9, and there is one more pair of pairs. Now from correspondence theorem we know, or from the results of this section, we know that because this is only this cyclic subgroup, okay, generated by 7, since this is a subgroup of U16, the codomain group, its inverse image under alpha itself is a subgroup of the domain group. That means this will be a subgroup of the domain group. Okay, so that is the inverse image. And there is one more part of that result which tells us that if the original group is normal, then its inverse image is also a normal subgroup in the domain group. In this case, however, everything is normal because the groups are abelian. And let me just end the video here itself. We are going to continue with the next things in the next Lie update. And tomorrow, as usual, we have our analysis. And tomorrow we are going to start a new section, the next one after those summation things. That is the section on uncountable sets. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.